Hello and welcome. This is an introduction to experiment 6. This experiment deals with the stabilities of substituted benzene compounds. And so getting a start here, this experiment was actually written as an introduction to WebMO, which you've probably already been introduced to in the previous experiment. I do want to point out that there's many different programs like Spartan, Gaussian Games, QChem, and others that essentially all run the same calculations as each other. So what's really most important is specifying your level of theory and your basis set. And then generally speaking, you should get very similar results no matter which of these engines you use to run your calculations. Um, okay, so the first part of our experiment deals with looking at the stabilities of benzene derivatives where we have chlorine atoms in the R positions. So 1,2-dichloro, 1,3-dichloro, and 1,4-dichlorobenzene. And so what you're going to do is just simply build each one of those molecules, evaluate their, do optimization frequency calculations so you can evaluate their delta E's, I should say delta E. I'll try to fix that. Delta E, delta H, delta G's in kJs per mole. What you want to do is try to figure out which one of those is the most negative, hence the most stable, and then figure out how much higher in energy the other two isomers are relative to that most stable isomer. What we're kind of doing here is getting a sense of how does a chlorine, atom on a benzene ring, where does it want to be relative to another chlorine atom to have the greatest stability? Okay, so then we'll also look at the xylene isomers. So xylene is just the dimethyl benzene. So you'll build the orthometaparo xylenes, and then evaluate also their delta E's, delta H's, and delta G's. And so then before the next lecture, those activities are the day one activities, and then you'll write a quick narrative explaining what types of calculations you ran, and then what the relative energies and really pointing out which isomer is the most stable for those compounds. The one thing I think I wanted to mention is that we will assign a basis set and a theory and a basis set to you that you're going to use essentially throughout this experiment. So one of your lab TAs or I will give you an assignment of your theory and basis set for this experiment towards the beginning, whenever you are set to begin it. Okay, day 2 is looking at the dihydroxybenzene isomers. Now the only thing slightly more complicated with the DHB isomers is that the dihydroxybenzene isomers have a local minimum problem. So if you imagine having your R group as a hydroxyl group, the hydroxyl group might want to point in the plane of the ring one way or the opposite way. So you're going to have, sort of 3 to 4 conformations that you could consider for your compound. So we'd like you to sketch those out so you get a sense of what those look like. The 1,4 isomers are going to simplify down probably just to 2. If you look at them by symmetry, you'll probably see that there's only 2 isomers for them. And then for these compounds, you're going to look with the same theory and basis set. You're going to look at their delta E's, delta H's, and delta G's like you did previously. We want you to kind of report and look at their dihedral angles so you can kind of get a sense of which ones are the most stable. You'll be preparing some tables that compare the relative energies for each conformers of each isomer. So a little nomenclature here. So conformer is a conformational isomer of a particular isomer. So if 2 isomers differ only by their conformation, then they're conformers of each other. And then if you look at 1,2 versus 1,3 versus 1,4, we would call those to be different isomers. So you will have 3 or 4 different conformations of each isomer. And the question is, which of those is the most stable for each isomer? And then the table 2 will help you examine of those global minima of each isomer, which of those is the most stable. So is the 1,2, the 1,3, or the 1,4 global minima more stable? So you can see here the local minimum problem is really important. You can't just look at one minima of each of the isomers. You have to really evaluate all possible minima so you can know which one's the most stable. So then you can compare amongst all 3 isomers of the DHBs so you can figure out which one's more stable. And then the last day of the experiment is looking at vanillin versus ovanillin. So look up those structures. I think you'll see that they have a hydroxy group, a methoxy group, and an aldehyde group. And so then you have the case of actually having several different conformations that are going to be possible for these isomers. So just sort of consider your in plane versus out of plane for your three groups and kind of go from there into thinking about how many different conformations you have. I think you're going to find that you have somewhere between 6 to 9 different conformations. Now, given that you have a hydroxyl group, you can probably imagine some hydrogen bonding. So you might be able to come up with a pretty good prediction of which one's the most stable or is likely to be the most stable. So, but we would like you to try to consider all possible conformations. And so then we'd like you to write and focus your final presentation on activities 3 and 4, um, the dihydroxybenzene and uh, the vanillin O-vanillin isomers. So there's some final things to consider for your final presentation and activities.